In Calcbc, we're looking at polar curves, day 1. We're used to plotting points with x comma y, where if you were to look right up here at the top of the screen, we can go x steps to the right or left, and then up y steps or down y steps. We will get to this point. There's another way to identify a point, though, and to represent it, not with a Cartesian rectangular coordinate of x comma y, but in polar coordinates, where you'd have r comma theta. And r would be your distance from the origin, from the pole as we call it, and theta would be the angle from the x-axis to this point in question. And just want to immediately draw your attention right here to this kind of a comparison. We can have the point x comma y. We're so used to seeing that. That's been our only experience of representing a point so far. Let's just say, for the sake of argument, it's in the first quadrant. We know that there's a distance from the origin called r. From the Pythagorean theorem, we'll know that r squared equals x squared plus y squared. Here's a link between polar coordinates and Cartesian coordinates. Likewise, we also look at this angle theta. Tangent is always the opposite over the adjacent. Tangent of theta is y over x. And very importantly, we also know from basic trig that we can say that the cosine of this angle, cosine of theta, would be the adjacent side all over the hypotenuse. That'd be x all over r. But that means that x is equal to r cosine theta. Similarly, we could say sine of theta is equal to y over r. And this is going to lead us to also know that y is equal to r sine of theta. What we have here are 4 very valuable links between the two systems. Let's just consider this point 2, 2. If we were to look at 2 comma 2, we're so used to going 2 steps to the right and 2 steps up. We could say here it is, here's this point 2 comma 2. But we could build ourselves a little triangle right here and say that our x distance is 2 and our y distance is 2. You can wonder what our r value would be. Well, the r value, you might remember from the 45, 45, 90 right triangle. If you had half of a square and a 45, 45 right triangle, we had a, and a root 2. Our r would be radical 2. And this, of course, would be pi over 4 or 45 degrees. So we could say this is radical 2 comma pi over 4. But we're going to be asked to list 4 polar coordinates for this. This is if this angle was a positive angle coming from the x-axis. We could also have a negative angle. And you can see that we'd still have a reference angle of pi over 4, but that would be negative 7 pi over 4 then, or just shy of negative 2 pi. What can be a very big surprise with polar coordinates is that we can also deal with a negative r value utilizing an opposite quadrant. I could say that I've got negative radical 2 comma. If we were here in this third quadrant, you could see that we'd still have a pi over 4 reference angle. And if this is pi, we'd go pi over 4 beyond that. Pi plus pi over 4 would be 5 pi over 4. Now, as you're looking at this, you're probably visualizing a third quadrant angle here. But the negative r value will project that point to the opposite quadrant. In other words, this point, negative radical 2 comma 5 pi over 4, is actually going to land right where 2 comma 2 is. We can also of course, have a negative angle. And you can see we'd still have that same reference angle of pi over 4, but we'd be pi over 4 short of negative pi. This would be at negative 3 pi over 4. So here are 4 different polar coordinates that all, if you were to graph them, would land you at 2, 2. Now, usually it's not so bad to go from polars to rectangulars. You look here, you have an r, you have your theta. And if we were to look at this, we can say, well, we know where pi over 2 is. We know that we're going to go 4 steps away from the origin or from the pole. You could say, well, I wonder what my x comma y would be. Your x comma y, you could see just visually that we're not moving right or left any, but we're moving up 4. I do want to point out something to you, that we could have done x is equal to r cosine of theta, and you would have seen this was 4 cosine of pi over 2. You could see very quickly that you'd get x is equal to 0. Pi over 2, cosine of pi over 2 is 0. Similarly, we could have done y equals r sine of theta. What's our r in this problem? It's 4. We've got the sine of pi over 2. This would just be a 4. You get the same thing. Here I'm just drawing a visual picture, and the other one is just using a formula. For b, it's very much a very similar kind of a setup. We could use those formulas. X equals r cosine of theta and y equals r sine of theta. You certainly may. I, however, would like to point out the negative r situation. We really need to see what's happening. Obviously, when we're looking at pi would be coming over this way, and a negative 3, you would think that you're going to be here on this negative x-axis, but the negative r actually projects this point 180 degrees in the opposite direction. It's actually going to land right here where I just drawn a dot. This is going to be the point 3, 0. Again, I just want to point out that you could have used this formula. X is equal to negative 3 cosine of pi. Cosine of pi is negative 1. You would see quickly that x is a 3, just like we saw. R sine of theta. Well, here we go again. You can say it's negative 3 times the sine of pi, but sine of pi is 0. Either way, whether you're using a formula or you're trying to get a visual perspective, you're going to get the same answer. I do want to show you that visual perspective. I think it's very important, and it will help you understand when things are getting graphed. Obviously, the formulas are the quickest, easiest ways. But let's draw this last one out. 5 pi over 6, if you think about that, that is a reference angle of pi over 6, and it's here in the second quadrant. Having negative 16 for your r, however, is going to project to the opposite quadrant. You're actually going to wind up in the fourth quadrant right here. Your x comma y is going to be this way. Now, I do want to point out the very famous 30, 60, 90 right triangle that can be at play here. Pi over 6 is equivalent to 30 degrees. And we know that opposite of 30 is a, opposite of 90 is 2a, opposite of 60 is a root 3. And it won't take you too long then to see that this is 8 and this is 8 root 3. However, because we're going down, we'd get negative 8. We'd have the point 8 root 3, comma, negative 8 for our Cartesian coordinates. I leave it to you to double check that if you did x equals r cosine of theta and y equals r sine of theta, you'd actually get the exact same thing. As we move on to example 2, find 4 different sets of polar coordinates for the given rectangular coordinates. Well, here we have 0, -4, and if we were to just go 4 steps down right here, you can see that your R would be 4 steps away. You could choose to be positive or negative, and you can see that this angle right here going from the positive x-axis is going to actually yield 3 pi over 2. So we could say 4, 3 pi over 2. Remember, this is our x, this is our y. It would only take a moment to see you've got a distance of 4 at this angle. You could also have 4, negative pi over 2, going with a negative angle in this direction. But the negative r tends to be the thing that kids are most concerned about. It's probably the newest aspect of this whole system. You would have to be 180 degrees away. So you'd actually have a point here with a negative r, then it would get projected right over to the point 0, -4. So this would be an angle of pi over 2. We could also say it's -3 pi over 2. I'm going to leave off B for the sake of time, trying to be good with time on this video. But as we look at number 3, just want to let you know that we can do a lot of work with our calculator. And just letting you know how we can do this, we're going to change our mode to polar. And when we hit polar, you're going to see that our windows change substantially. I'm going to just click this right here. I'm going to have y equals. We'll say 4 sine. Now the x button no longer is going to yield an x. It's actually going to yield a theta here. Do want to let you know that the biggest our x or y values could ever be, if you think about it, sine can only be as big as 1. My advice is to maybe have our x and our y values get close to that. I'm going to have x being equal to -5. Come down here and we could get a 5, and we can do the same thing down this way. Now as we're cleaning this up, you can hopefully see that we can get a very fast graph. When you hit graph, you're going to be able to see that as this thing is working out, well, you know what? I think our mode was wrong. Here's another thing for all our physics friends. Watch out. Your mode should always be on radians. And that's actually something that slowed us down quite a bit. So as we're graphing that, you can see it sure looks like we're getting something almost looking like a circle. And it's looking something like so. Okay, you can see if I let theta equal pi over 2, you could see that our r would actually be going up to 4. And you can even think about working it out in that regard. So let's take a look at the sine of 6 theta. If we did that real quickly, we'll delete the 4, come right here and do 6 theta. Again, maybe we want to change our window. Right now, the biggest that sine could ever get to be is a 1. And at that point, what we have to be careful about is in our window, we might want to make this go to -2, come down here to a 2. I have our y min go to a 2, -2, and a 2 as well. And, as we hit graph here, you can see that we get a little bit of a surprise. In fact, perhaps it's quite a big surprise as we're looking at this. This sine of 6 theta, you can see we've got a multi-petaled rose. And that's something that we shouldn't be too shocked to see. So these pictures can get to be rather nice looking. And we'll definitely be picking up with that soon.